We've reached Module 11, and this is kind of what I like to think of as the home stretch of the course. And it's perhaps useful to take a look back and see essentially where we've come from. Remember, in the very beginning of the course, we were essentially learning about naked eye astronomy, why the sky moves the way it does, why the moon has phases, all that kind of stuff. Then we took a little detour and we learned about the sun, we learned about light, we learned about the sun, and essentially how our solar system came to be. And then we put our sun, all that stuff is still pretty close to us, right? It's pretty close to home. Then we talked about how the sun compares to the other stars, and particularly the stars in our own galaxy, the Milky Way galaxy. We talk about the evolution of stars, that they do indeed go through life cycles. They are formed, they spend a long time on the main sequence, and then they die in various ways. Quite often winding up as either white dwarfs or neutron stars, black holes. We talked about supernovas, all that kind of stuff. Now we are going to climb the cosmic distance ladder. In fact, that's the title of the lab activity you're going to be doing with this module, because we're going to now learn about stuff that's not just within our own Milky Way galaxy. We'll talk about the Milky Way galaxy. In fact, chapter 17 is about the Milky Way galaxy. And we'll learn how astronomers figure out the distances to objects within our own galaxy, as well as we're going to learn how astronomers find the distance to galaxies outside of our own, because it turns out that 100 years ago, when we were just barely discovering that we were in a galaxy, it was thought that Milky Way galaxy was it. But it turns out, as we've learned as technology has improved, we've had better telescopes, that our galaxy is just one among billions of galaxies out there. And so we're going to learn how astronomers determine the distance to these different galaxies. We're going to learn the properties of some of these galaxies. That's the topic for chapter 18. So, like I said, a lot of ground to cover in just 2 chapters. Okay, so if you've ever been observing the night sky, especially in a dark location, you have seen the Milky Way. It's essentially that milky-ish patch through the sky, or that band through the sky, that is seen from a dark location. And it's essentially the collected light from all the stars that are in our particular spiral arm of the Milky Way galaxy. But one thing that's really important for you to understand is that when you look up in the night sky with the naked eye, you are just seeing stuff within our own galaxy, with the exception of one object. You may see a very small fuzzy patch in the constellation Andromeda. What you're actually seeing there is an object that is outside our own galaxy. It's a relatively near neighbor called the Andromeda Galaxy, M31. And this is the only thing you can see with the naked eye that does not belong to our own galaxy. It's actually outside our own galaxy. It's a galaxy unto itself. So what looks like a little fuzzy patch in the sky to the naked eye actually is the collected light of 100 billion or so, 200 billion stars that make up the Andromeda Galaxy. It's sometimes said that we know less about the oceans or the interior of the Earth than we do some of our nearest neighbors in space, like the Moon or Mars. And that's partially true, because it's really difficult to go to the bottom of the ocean and explore. It's even more difficult to go into the interior of the Earth and explore. It's a little bit easier to kind of send a probe out and perhaps look back at the Earth or look at the Moon, that sort of thing. Same issue with the Milky Way galaxy. We know less about the actual structure of our Milky Way galaxy than we do, some other galaxies, because we are in the Milky Way galaxy. That's a little bit more difficult. We've never sent a probe out far enough to turn around and take a selfie of our galaxy. In fact, we've barely sent our farthest probe is just outside of our own solar system. I remember that would be like the Voyager probes that were launched back in the 70s. They've barely gotten out of our own solar system, much less gotten out of the Milky Way galaxy and been able to turn around and take a selfie and then send that information to us. Remember, that would have to be a trip of hundreds of thousands or 100,000 light years or so in order to really encompass the entire galaxy. So anyway, that's part of the problem, is that we're inside. So we can't get an overall view of the Milky Way galaxy the way we can, say, the Andromeda galaxy, because we're outside of the Andromeda galaxy. We can see the entire thing. Another difficulty is that there's a lot of gas and dust, so it's tough to see the center of the galaxy. And another difficulty is distance measurements. But one thing that we're really going to be focusing on this module is the different tricks that astronomers use to determine the distances to objects. And again, like I said, that's the theme of the lab activity for this module, is the cosmic distance ladder. We'll climb the cosmic distance ladder using different techniques to determine the distances to objects, not only within our own Milky Way galaxy, but also to distances to other galaxies. Again, it never ceases to amaze me the physics that goes into astronomy. So one way of determining the distance to objects is to observe, and especially to determine the distance to other galaxies, is to use what are called Cepheid variable stars. These are stars that don't stay the same brightness. They tend to vary in their brightness, and that's what we're seeing here. We're seeing the light curve, the visual magnitude. So this is essentially how bright these stars appear from Earth. And this particular star does vary in its visual magnitude. But the nice part is that it varies in a consistent way. Over this time period, it goes from being its dimmest to its brightest and back to its dimmest. And that's nice because once we're able to determine that period, it turns out that the period of a variable star like this is related to its luminosity. And once you know the luminosity, remember luminosity is essentially absolute magnitude. Once you know the capital M, and we already know the little m, once you know those two things, you can determine the distance by using what's called the distance modulus. And again, we'll get practice using that equation. It's not something you have to memorize, but it is useful in determining the distance to, in this case, the star. And of course, the star is just located within a galaxy, so if you know the distance to the star, you know the distance to the galaxy. So as I already mentioned, we don't have a selfie of the Milky Way galaxy, so how do we know what it looks like? Well, it's kind of like if you don't have an overall picture, but you can start to fill in some of the pieces, it starts to take shape, and that's the way essentially astronomers do it. They first of all try to find bright objects and use different techniques to determine the distance to those objects and their directions of motion. They can use also different wavelengths outside of the visible, because with visible you do get a lot of gas and dust that gets in the way and blocks visible light. So that's another strategy for determining the distance and direction of other objects. And once you've started to find out those distances and the directions of motion, the overall picture begins to take shape. Even within a galaxy, you'll find clumps essentially of stars. Some are closer packed than others, and when you have a lot of packing of stars, we call those clusters. And there's two different types of clusters: open clusters and globular clusters. Open clusters are not as dense. There's not as many stars per unit volume in an open cluster compared to a globular cluster. And it turns out that open clusters tend to, at least in the Milky Way galaxy, and we assume in other galaxies as well, they tend to be within the disk of the galaxy. So when you find open clusters, they typically are within the galaxy's disk. When you start to find globular clusters, they tend to be outside of the disk area and more in what's called the halo. Now, if you ever get a chance to look through a telescope, I encourage you, whoever's operating the telescope, to check out the double cluster. The double cluster is in the constellation Perseus, and it's a good example of open clusters. You actually have two open clusters relatively close together. So what looks like to the naked eye just kind of a fuzzy patch in the sky, when you put a telescope on that fuzzy patch, you're going to see hundreds of stars popping into view, which is really quite breathtaking. Now, I sort of put the cart in front of the horse in the last slide by mentioning the fact that the center of the galaxy is in essentially in the constellation Sagittarius. How do we know that? Well, it turns out that Shapley, who did a lot of the research on star clusters, particularly globular clusters, when he started to plot them, realized that the globular clusters are not distributed evenly around the sun. In fact, they're distributed evenly around a different portion of the Milky Way galaxy, and that's how he determined that that location must be the center of the Milky Way galaxy. And it's essentially, like I said, in the constellation Sagittarius. It is very difficult to research it using visual observations, because when you're looking toward the center of the galaxy, you're looking through not only billions and billions of stars, but all kinds of gas and dust and that sort of stuff that obscures the view. So quite often researchers have to use different forms of radiation in order to to peer into the center of the galaxy. Okay, so now we're finally getting a pretty good feel for the structure of the Milky Way galaxy. First things first, the size of the Milky Way galaxy. You're going to see varying numbers for this because there is no real definite boundary. It's kind of like, asking, where does the solar system end? Or, there is no marker out there in space saying you're now entering the Milky Way galaxy, you're now exiting the Milky Way galaxy. You're going to see values anywhere from 75,000 light years in diameter to upwards of 100,000 light years in diameter. Notice where the sun is located. We're about 2/3 of the way out from the center of the galaxy. So we're not necessarily at the center of things. We're a modest distance out. We are located along the disk of the galaxy. Remember, we talked about the fact that we have the disk of the galaxy, and then you have the halo section of the galaxy. So we are in the disk. We're actually on a spiral arm of the disk. And as mentioned already, most open clusters occur in the disk part of the galaxy. Globular clusters tend to be located in the halo portion of the galaxy. And one thing that makes a galaxy is, remember, a galaxy is just a collection of billions of stars, and they are gravitationally bound to a center. So there's a galactic center. We say it's in the vicinity of the constellation Sagittarius, and all of the stars appear to be bound to this galactic center, and they orbit around. Well, it turns out that our sun takes about 240 million years to orbit one time. So if you recall, our solar system is about 5 billion years old. So that means that we've been around the track about 20 times or so in the lifetime of the solar system. Another thing that's relatively interesting about the motion of the stars in the Milky Way galaxy is, well, first of all, think about the orbits of the planets in our own solar system. Which one orbits fastest around the sun? Mercury, right? We saw that, and in fact, Kepler figured out the fact that as you get farther and farther away from the star, in this case our sun, the longer it takes for that planet to orbit. And so you would expect that stars that are close to the galactic center should be moving very, very quickly, and stars that are moving farther away from the galactic center should be moving much more slowly. That's what you would expect. Flip the page to find out what's the reality, the reality of the situation. Okay, so as I mentioned, you would expect when you start to plot the velocity of stars with respect to their distance away from the center of the galaxy, you would expect to see this kind of a relationship, the Kepler kind of relationship, where as you increase the distance, the star should be moving slower. In reality, with the measurements that have been taken, you actually see this curve here, which does not show that decrease in velocity with distance from the center. So it turns out that stars in the Milky Way galaxy do not behave according to what Kepler would expect, and that means that there must be something else going on. There must be some sort of other gravitational force apart from just the gravitational attraction of the center of the galaxy at play here. There must be mass, there must be matter that we have a hard time detecting, which is influencing the orbital velocity of stars. And it turns out this winds up being dark matter, which we'll have more to say about in the next module. And then actually, it should be noticed, a huge surprise that all stars are not the same age. But how do you age? How do you determine the age of a star? Well, one way of doing it is by looking at the absorption spectrum of the star and seeing its composition. Because it turns out that stars that are made up mostly of hydrogen and helium have got to be old stars. They must have been made early on in the universe. Shortly after the Big Bang, when the Big Bang first occurred, all that was around was essentially hydrogen and helium, mostly hydrogen and a small amount of helium. And that's what the first stars were made from. And so if you have an absorption spectrum from a star like that that is made of just hydrogen and helium, it shouldn't have much in the way of any other absorption lines apart from hydrogen and helium. Stars that were made late, now of course those are early stars, especially the ones that had short lives, those really hot ones that lived fast and died young, when they exploded, when they went supernova, they spewed their enriched guts. Remember, we've talked about the fact that as a star goes through its dying process, it generates other elements beyond hydrogen and helium. And that is what in astronomy we call them metals. So anything heavier than helium is considered to be a metal. And so it spews its enriched guts, which include metals heavier than helium, into the interstellar medium, from which new stars are created. So that next generation of stars will have hydrogen and helium, but they'll also have small percentages of those heavier elements. And the more generations that occur, the more enriched the interstellar medium becomes. And so the younger a star, the more recently a star has formed, the more you would expect it to have metals as part of its composition that would be picked up in an absorption spectrum. So population 2 stars are your really old ones that are what are called metal poor. They're mostly hydrogen and helium. Population 1 stars are recently formed stars that were formed from interstellar medium that had the enriched guts of generations of stars that had exploded before as part of the interstellar medium. So population 1 stars, you would expect to be metal rich. Okay, so one thing we've discovered is that the Milky Way galaxy is what's called a spiral galaxy. We'll talk more about the different types of galaxies in the next chapter, but for the time being, let's just think about why we have these spiral arms that make up the Milky Way galaxy. And it turns out that, of course, the spiral arms are areas where there's a lot of stars, in fact, new stars, very, very bright stars are showing up. And those stars are, of course, forming from gas and dust. That's what stars come from. So there must be something that's triggering gas and dust to become stars in these spiral arm areas, as opposed to other parts of the Milky Way galaxy. We'll talk about that on the next slide. Okay, so I encourage you to check out page 381 in your textbook to explain why we have spiral arms. There's a theory called the spiral density wave theory, and I encourage you to check that out, that description on page 381. But one way of thinking about why stars appear to form in these spiral arms is to think about like a traffic jam. Like if we were looking from above, seen from an airplane, a traffic jam would look quite stable. You're seeing cars slowing down, just moving down the highway. The individual cars in the jam would constantly be changing, but the traffic jam would be essentially a stable pattern moving at its own speed along the highway. If you've got this tractor, it's going to continue to move, and cars are going to continue to jam up behind it, and then they're going to move, they're going to zip around, and so the jam will always be there, but the cars that are participating in the jam will be constantly changing. And that's essentially what's happening in these spiral arms, is that the gas and dust is actually rotating faster than the density wave. But as that gas and dust moves into that density wave, it's like having that shock wave that's able to spur star formation. So the gas and dust is just gas and dust, but it gets triggered when it moves into these density waves to actually start forming stars. And of course, the stars that are the ones that, the hottest ones are the O's and B's. Those are the ones that are easy to see, and they also live very short lives. So it's indicative of spiral arms that they are indeed star-forming regions, because you see old stars distributed throughout the entire disk of the Milky Way galaxy. Where the O's and B's are seen is only in the spiral arms themselves, because O's and B's have relatively short lifetimes.